Welcome to Microlecture 30. We're going to be talking about molecules with more than one chirality center. We're going to be introducing the terms diastereomer and meso compounds. Okay, so I'd like to talk about molecules with more than one stereocenter now. So these types of molecules can be enantiomers, so that is, they can be non-superimposable mirror images that we've talked about with compounds that contain one chirality center. But if they're not enantiomers, then what they are, usually with respect to one another, is diastereomers, and that is just simply stereoisomers that are not enantiomers of one another. So let's do an example where we have a bromine and a chlorine situated on a cyclopentane ring. Hopefully you can see that this is a stereocenter and that is a stereocenter. And one trick for figuring out how many stereoisomers that you can have is to take 2 to the n power, where n equals the number of chirality centers. And so I'm expecting for this compound to see 2 to the 2, since there's 2 chirality centers, or 4 possible stereoisomers. So let's think about what those could be. So first of all, I could have the bromine on a wedge and the chlorine also on a wedge. Another possibility is that I could put both of those groups on a dash, so back. Another possibility is that I could put the bromine facing forward, coming out at you, and the chlorine back. And then lastly, I could have the bromine back and the chlorine coming out. So these are all of our possible stereoisomers, all 4 of them. And so we want to start thinking about how these different stereoisomers are related to each other. Are they enantiomers of one another? Are they diastereomers of one another? How do we tell? First of all, let's just do a little bit of practice and determine whether this first compound in the upper left-hand corner is whether it contains R stereocenters or S stereocenters. So pause the video real quick and see, just for that very first molecule, not all of them, if you can assign the R or S stereo configuration. All right, so when you're assigning the stereo configuration, that involves ranking, prioritizing. I'm going to call the bromine priority number 1. It has a larger atomic number than the carbon here, and this carbon is a greater priority than the other one because carbon number 2 goes to a chlorine atom, so it's going to win in the priority rankings. And so 1 to 2 to 3 is a counterclockwise direction. And in addition, I wasn't too worried here about the hydrogen atom, but it's good to just remind yourself of where that is, and it's pointed back right where we need the lowest priority group to be. And so that is indeed, so clockwise is R, an R stereocenter. Do the same thing with the carbon that contains the chlorine atom, and you'll see that this is a stereocenter that's going counterclockwise, therefore S. Okay, so we have an R stereocenter and an S stereocenter in that first molecule. Hopefully you got the same assignments as I did. And so I want to teach you a little trick. If you have stereoisomers and you've already figured out the stereo configuration of one of the stereoisomers, you can figure out the other ones as long as they're drawn similarly. And these ones are. It's pretty easy to see then that the bromine pointed forward is still going to be an R stereocenter in this molecule. When we put the bromine in the back, we change the stereoconfiguration at that stereocenter, and so these are going to be S. All right, likewise, the chlorine pointed out at you is S, and therefore this last molecule has an S stereocenter there as well. But if we flip if we swap the hydrogen and the chlorine atoms with each other, we invert, if you will, that stereo configuration from S to R. So these would be R. Okay, so you don't have to assign all of them, which can take quite a bit of time and brain power. You can assign the rest of them based on your assignments for the first. So we want to ask the question, which one of these guys is the enantiomer of the first one, right? So if I call this A, this compound B, this one is C, and this one is D, which is the enantiomer of A? What we want to do, knowing that it's a non-superimposable mirror image, is draw the mirror image of this compound. All right, and so if this is my mirror plane, this molecule is looking at itself in the mirror, then what I'm going to have is, I didn't quite give myself enough room there. And what I'm going to have is the bromine and the chlorine pointed outward, like so. So those are mirror images. They're also non-superimposable. But it doesn't look anything like the molecules above, so I can't really tell necessarily just looking at this which one it lines up with, B, C, or D, right? So which one is this? The best way to tell is to flip the molecule in three-dimensional space. So if you had the molecular model, this would just be rotating it around until you have the bromine pointed back and the chlorine pointed back. So you're flipping the molecule. And so everything that was on a wedge is now on a dash. What was pointed forward is now pointing backward. All right, and now it's pretty easy to tell that this is compound B. All right, so A and B are enantiomers. All right, and so we can tell, which one is the enantiomer that way. And another sort of trick or shortcut is for you to be able to just know based on the stereo assignments, so the stereo configurations, whether they're R or they're S. So enantiomers, for enantiomers to be enantiomers, all of the stereo configurations must change, so R to S and S to R. So enantiomers means all of the S become R and R become S. It's a true opposite. So if you think about it, like the larger molecules that we practice on, like prednisone that had 6 chirality centers, if I wanted to draw the enantiomer of prednisone, I would have to change all 6 stereocenters from S to R or R to S. And so anything that doesn't qualify as that then is going to fall under the category of diastereomers. All right, and so we can see then that the relationship between A and B at the top, going back up to the top, is that R switched to S and S switched to R. All right, and so we can see that those two are indeed enantiomers of one another. that means that A's relationship with D or C would be that of a diastereomer. You can only have one enantiomer. All right, so we can kind of think about the relationships between the other compounds as well. The relationship between C and D is such that all stereocenters have changed. So these are also enantiomers of one another. Okay, and so and diastereomers then are stereoisomers in which not all stereocenters have sort of flipped from R to S or S to R. All right, not all of them, so less than all of them, and that would make it a diastereomer. And then there is one more class of molecules that have more than one stereocenter, and this is a special class, it's a special case that we don't see too often, but that is a molecule that has an internal plane of symmetry, like the one shown here. All right, so when you have a molecule with an internal plane of symmetry, it has no enantiomer, right? Because the enantiomer is an identical compound. And so again, these are called mesostructures. And so let's do an example here. If I have a cyclohexane ring and I've got two methyl groups, and we can clearly see that we've got a couple of stereocenters here. Let's try to draw the mirror image. So this molecule is kind of looking at itself in a mirror plane. And so you see what we get is the same exact drawing. So these molecules are the same. They're superimposable. They're mirror images, but they're superimposable. And so they are not enantiomers. Okay, and so let's do another example. So maybe we have a couple of bromine atoms, and they're both pointed backwards, and this molecule is looking at itself through a mirror. What it's going to see in the way of a mirror image is the exact same molecule. Okay, so these structures were meso, these structures were meso. They're not two different compounds, they're the exact same molecule. It's a little bit more difficult, a little bit more challenging when the two groups are not facing the same way. So in other words, they're not cis to one another. So let's draw an example of a trans mesostructure, and I'll show you how to think about that. So if I have an OH group on pointed out at you and then one back into the plane, and this molecule is looking at itself, then I need to draw its mirror image like this. All right, and it's kind of hard to tell if that is the same compound or not, so we're going to do the flip trick and just kind of rotate the molecule around its center axis. And so that means the OH that was pointed backwards is now going to be pointed forward. The OH that was pointed forward is now pointed backward. So again, rotating the entire molecule, if you have a molecular model built of this, just rotate it around. Just like you're rolling a rolling pin here. And again, these are the exact same. Okay, so these are superimposable mirror images. They're the identical molecule, and that makes them meso. Mesostructures are achiral. They do not bend plane polarized light. They're optically inactive. Okay, to use a couple of vocabulary words, achiral means not chiral. So it's an unusual case, right? We've got stereocenters in the molecule. We have chirality centers, but the molecule as a whole is achiral.